Hello and welcome to the Unit 8 Section 4 video on segments and circles. So in the last section we talked about angles. This section we're going to talk about segments. So let's start with the chord-chord product theorem. The following theorem describes the relationship among the four segments that are formed when two chords intersect in the interior of a circle. So we talked a little bit about how we relate the angle with the arc lengths for angles in the last section. But if we take the two chords that intersect at E here, then we can then say that the length of AE times the length of EB is equal to the length of CE times the length of ED. So basically you're going to take the two segments of each chord, multiply them, and set them equal to each other. So in example 1 here, we want to find the value of X and the length of each chord. Okay, so to find the value of X, we're going to take PQ and we're going to multiply it by QR, and then we're going to take SQ and multiply it by QT. So PQ is 6, QR is 4, SQ is X, and QT is 8. So we have 24 is equal to 8x, and so x is equal to 3. So to find the length of each chord, PR is 6 plus 4, which is going to give us 10. ST is going to be X, which is 3, plus 8, and that gives us 11. So the math isn't terribly difficult, you just need to know the relationships. In example 2, archaeologists discovered a fragment of an ancient disk. To calculate its original diameter, they drew a chord AB and its perpendicular bisector PQ. We want to find what the disk diameter was. Okay, so PR here is going to be the diameter. So to find out what this is, we are going to take AQ and multiply it by QB. And then we're going to take PQ and multiply it by QR. Well, AQ is 5. So is QB, because we bisected. PQ is 3, and we're going to find what QR is, which is the rest of the length of this diameter. So we have 25 equals 3 QR. Divide each side by 3, and you get 25 over 3. QR is either 25 over 3, or you can also say 8 1/3. Okay? So to find the length of the whole thing, we have PR is equal to 3 plus 8 1/3, and that gives us 11 1/3 inches. The secant-secant product theorem states that a segment of a secant with at least one endpoint of the circle. A secant segment is a segment of a secant with at least one endpoint on the circle, because we talked about secant line being a line that goes on forever in both directions. Now we're going to take a segment of that secant. An external secant segment is a segment that lies in the exterior of the circle with one endpoint on the circle. So here, PM, NM, KM, and JM are all secant segments of circle Q. NM and JM are the external secant segments. They are the ones that lie on the outside of the circle. A little bit of vocabulary to set up our next theorem. If two secants intersect in an exterior of a circle, so here secant AE and CE, they intersect at E here, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So in other words, the whole times the outside part is equal to the whole times the outside part of the other one. Okay? So let's take a look at example 3 here. We're going to find the value of x and the length of each of the secant segments. So here we have RT, which is the whole thing of this top one, and we're going to multiply it by RS, which is the exterior part. That's equal to RQ, which is the whole thing of the other one, and we're going to multiply it by RP, which is the outside part. So RT, the whole thing, is 6 plus 4. 6 plus 4 is 10. RS is 4. RQ is 5 plus x, or x plus 5, because that's the length of the whole thing, times 5, which is the length of the outside part. And so we multiply this side, we get 40. Distribute this side, you get 5x plus 25. Subtract 25 from each side, you get 15 equals 5x. And so 3 equals x. So RT is going to be equal to 4 plus 6, which we already determined is 10. RQ is equal to 5 plus 3, which is 8. Finally, we have the secant-tangent product theorem. A tangent segment is a segment of a tangent with one endpoint on the circle. AB and AC in this figure are tangent segments, and we mentioned these types of tangent segments a little bit earlier. So in this figure, you know that AB is congruent to AC. Let's talk about the theorem. If a secant and a tangent line or tangent segment intersect in the exterior of a circle, then the product of the lengths of the segment and its external segment equals the length of the tangent segment squared. So in other words, the secant part behaves exactly like what we just described, the whole times the outside. Then you're going to take the tangent part and square it. So let's do an example to show how that works. So here we want to find the value of x. Well, let's take the secant part first, the whole, which is SQ, times the outside part, which is RQ, is equal to PQ, which is the tangent part, squared. So SQ, the whole thing, 5 plus 4 is 9, times RQ, which is the outside part, which is 4, is equal to x, which is the tangent part, squared. So 9 times 4 is 36. And so we have plus or minus 6 is x. But the value of x must be positive 6, since we cannot have negative length. So we'll just take off the plus or minus, and we'll just say x is 6 in this case. So remember, a lot of times you're going to have to think about what you have here. You have to think about what value makes sense. Can we have a negative value in this context? All right, so that pretty much wraps up what we have to talk about with segment lengths. Coming up in the next section, we're going to talk about equations of circles.